Chapter 2 homework problems. They were due on September 3rd. So problems 7 and 10 were related to each other, which is why I assigned both of them. So to find the displacement of this object during the time interval indicated, which is from 0.1 to 0.3 seconds, you need to get the area of the graph. So the area of a triangle is pretty simple. It's 1/2 base times height. So the base was a time interval of 0.2 seconds, and the maximum height was 0.8 meters per second. So that gives me 0.08 meters, and I think they asked for it in centimeters, so that's 8 centimeters. To find the acceleration, I need to find the slope of the graph here and the slope of the graph here. So from 0.1 to 0.15 seconds, I had a change of 0.8 meters per second, and then that time interval was 0.05 seconds. So they gave me 16 meters per second squared. From 0.15 to 0.3 seconds, I go from 0.8 meters per second back down to 0. So this is final minus initial velocity, final minus initial time. So it gets me negative 5.3 meters per second squared. For problem 20, the way that I thought about this was if you threw a ball up at 20 meters per second, to find the velocity after 1, 2, 3, and 4 seconds. Actually, I think it was asking about the final velocity and then the time to take to do that. So you could think of basically the last 10 meters of flight, and because at any particular point location that's the same elevation for a projectile, the velocity up would be the same magnitude as the velocity down, just opposite direction. So really at this point at ground level, when it's moving back down, it's moving 20 meters per second and it has to go 10 meters. So I use this formula, which is one of the first 3 kinematics formulas. 20 meters per second, square that. 10 meters per second squared is the acceleration, and then it's going to fall 10 meters. So that tells me that the very bottom of its path, it's going 24.5 meters per second. To find the time up and time down, I could have done things like realize it's going to take 2 seconds to get to the top of its path, 2 other seconds to get back down to ground level, because our rate of change of speed is 10 meters per second per second. Or I could simply do this. I could simply say that the total, basically my final velocity is equal to initial velocity plus acceleration times time. And because one of these quantities is up and one of these quantities is down, at least one of each, I have to think about positives and negatives because that actually matters. So I chose down as being positive. So that was my final velocity. My initial velocity was up, so that I made that negative. Acceleration is down, so I made that positive. And that gave me a time of 4.45 seconds. As I indicated in purple, there's lots of ways to do that. For problem 27, this is the graph that you were given, and it was either position, velocity, or acceleration graph. And for position graph, the velocity, I could look and see what the slope was at that point. And at 7 seconds, the slope was negative 10 meters per second. To find the velocity, if it's a velocity time graph, I simply went across and looked at the velocity, looked at the y-axis value, that is, at 7 seconds, and that was negative 20 meters per second. For acceleration, it indicated that we started off with 10 meters per second. I think we were told that. So then we would use the area of the graph to find the change in velocity. And initially I screwed this up because I was thinking, oh, this area would cancel out that area. Well, it would if we were talking about 8 seconds in time, but we're only talking about at 7 seconds. So this area here does not cancel out this positive area here. So essentially what I had to do is do a bunch of work to think about the fact that the time from 5 to 7 would actually equal the time from 3 to 5, or pardon me, the change in velocity would be the same. So then I was looking at the change in velocity during the first 3 seconds. So I looked at the area of the graph during those first 3 seconds, and I ended up getting an area in a graph of 6.5 boxes, and therefore that translates to 65 meters per second. So if I was already going 10 meters per second, that means my final velocity after 7 seconds is 75 meters per second. 39 we talked about in class. It's got a negative velocity. I think it has to be moving to the left. Positive acceleration. In this particular case, oh, that's interesting. I think I might have screwed that up. I think I might have been down. Nah, positive acceleration. I'll have to talk about that in class tomorrow. We're going to finish talking about that. I think this is pretty consistent. I think that's actually the answer the book has, but it's a little odd because here we're assuming that downward is positive, I guess, but we're also assuming that rightward is positive. A little bit annoying. Okay, we'll talk about that. 49. This is a problem that had multiple parts. So part 1, part 2, and part 3. Part 1 is when it's moving upward and the engine is on. Part 2, it's still gliding upward but the engine is off. And part 3 is going to be when it's only under the influence of gravity, so it's in free fall, and it's moving down. So to answer the first part of this, all I need is, for part A, I need parts 1 and 2. That gives me the maximum height. And we go from there. And I think morning announcements are going to come on soon. I did use a graph for part C to confirm what I had here. The total time going with the rockets on was 30 seconds. Time to reach the top was, I believe, 90 seconds. And then the time to fall back down was 104 seconds. And I did this one in class already also. So you could think of this a couple different ways. Use this to get the acceleration of g sine theta downhill, and use that to solve for the length. I'll use the trig, over here to solve for the length, which is h over sine theta. Note, the physics works whether you use energy or kinematics. So hopefully that helped out. I'm going to upload this now.